Ladies and gents, welcome to this week's Geotalk. Thank you for joining us. It's great to have you all online. Just to let everyone know that we are also streaming live on YouTube. So if you have anyone that would like to watch on YouTube, let them know. You can catch it on our Geotalk channel on YouTube, Wits Geosciences on YouTube. Right, so today we have Loic Lebras, who joins us for this talk. Thank you, Loic, for agreeing to give this talk, which is based on his PhD work that he did at Wits. But let me first introduce Loic. He hails from France, where he did his undergrad and MSc in geology. And then he joined the Helmholtz Institute in Freiburg, where he worked as a research scientist for several years before joining us here at Wits to work on his PhD, which is the topic of tonight's talk, on the metallogenesis of the Phalaborwa complex, using some really novel isotope systems and other geochemistry that you'll see. And Loic, very importantly, has spent a lot of time in our Wits Isotope Geoscience lab developing some of the methods for iron and copper isotopes that you'll see tonight. So great applause to Loic for doing that. That's a big job and a technique that's of benefit to the whole country and to Southern Africa as a whole. And you'll hear more about those techniques this evening. And of course, before we hand over, well, first I should end off by saying that Loic is now a postdoc here at Wits, so he's continuing with several different aspects of his research as a postdoc funded by Chimera here at Wits. So Loic, it's great to have you still in the team. Of course, we want to thank CCIC Group for hosting us, for hosting this Geotalk online and all the associated technology that goes with it. So thank you, John and the team. And we're going to hand over to Loic straight away. So Loic, do you want to, let me just stop sharing my screen. And Loic, you can share your screen. And unmute, of course. Loic, we can't hear you yet. You will need to unmute. No, I can unmute you. Okay, Loic, can you hear us? Can you speak?
Yep.
There we go. We can hear you loud and clear.
Somehow the presentation doesn't work. Oh, crap. PowerPoint just crashed.
Okay, that's no problem.
Oh, yes, it is. But
you'll enjoy your...
just let me start everything again.
In the meantime, whilst you're getting that loaded, Loic, I can just tell the audience that next week's talk is by Alan MacDonald, who's from the British Geological Survey, and he'll be speaking about groundwater recharge in Africa. Obviously, a very important topic, given the precious resource that groundwater is in Africa. And so that should be a very interesting talk. But now for the main action today, and that is Loic Lebras speaking about the sources and metallogenesis of the Phalaborwa igneous complex. So Loic, we can see your screen and we can hear you. So
awesome.
Over to you.
Thank you very much, Grant, and thank you everyone for attending this talk. So as Grant said, today I will talk about my PhD project, which consisted in the characterization of Cu-sulphides from the Loic carbonatite phosphorite intrusion using textural investigation, copper and iron stable isotopes, as well as trace element analysis. But first of all, I would like to talk a little bit about phosphorite and carbonatite intrusions. So maybe first, a phosphorite is a rock mainly composed of magnetite, apatite, as well as some silicates and calcite, and it occurs systematically with carbonatites. So it's a unusual rock, but it can be found everywhere around the globe. So with point pointer? Yeah, in Brazil, for instance, with Araha and Salit complexes, Nemigosenda Lake in Canada, in Africa as well, in all the eastern part with Phalaborwa and Star, of course, but also the Shield complex, Dorowa in Zimbabwe, Panda Hill in Tanzania, Bukusu in Uganda, in Kazakhstan and Yakutia as well. But the most important area about carbonatite phosphorite intrusions is Kola alkaline province here in Russia, also a little bit in Finland. And yeah, the one intrusion is very often compared to the Phalaborwa igneous, the Phalaborwa carbonatite phosphorite intrusion, is the Cough door complex because of the similar geometry. I don't really like this comparison. I'd rather compare the Phalaborwa carbonatite phosphorite intrusion to the three intrusion here in blue, so Nemigosenda Lake, Issei, and Abarastach. For one simple reason is because of the ring shape of the intrusion, which indicates a very similar emplacement process for both carbonatite and phosphorite, which is in the for Phalaborwa very important parameter for the formation of for the production of the different sulfide texture we can actually see within the pipe. Also, something which is commonly said is that the Phalaborwa carbonatite phosphorite complex is only occurrence of carbonatite phosphorite hosting copper sulfides. It's not entirely true. For instance, Salmagorsky ring in the Kola Peninsula also hosts sulfides, but at a very small concentration, and it has been proven that it precipitated from late-stage crustal fluids. So maybe I would like to add a small precision, is that the Phalaborwa carbonatite phosphorite intrusion is the only worldwide occurrence where copper sulfides occur at concentration of economic interest and where it is possible to find magmatic sulfides. So concerning the Phalaborwa igneous complex, it intruded into the gneisses and granitoids of the Cabval Craton, about 5 hours drive in the northeast of Johannesburg, and is characterized by the alignment on the north-south axis of 3 distinct intrusive centers. So the northern one, the central, which will be further referred to as the Loic pipe, and the southern intrusive center. As you can see on this geological map, the Phalaborwa igneous complex results from the successive intrusions of several magma pulses ranging to mafic at the contact with the gneisses and granitoids of the Cabval Craton to alkaline in the center of the Loic pipe. The first magma pulse emplaced feldspatic pyroxenite, which forms an aureole around the igneous complex, and also triggered a phenetization of the host rock, of the rocks of the Cabval Craton. And the second pulse emplaced the big unit of micaceous pyroxenite, which actually constitutes a major part of the Phalaborwa igneous complex. Post-dating the micaceous pyroxenite emplaced in all the 3 different intrusive center, pyroxene-bearing pegmatoids, and in the Loic pipe, a series of alkaline rocks, which are phosphorites and a couple of carbonatites. So the first rocks to emplace in the Loic pipe were an alternance of carbonatite and phosphorite. As you can see, there is this alternation of layers of phosphorite and carbonatite, with the phosphorite preferentially placing along the contact with the host rock, while the carbonatite preferentially emplaced towards the center of the intrusion. This carbonatite in red will be further referred to as bonded carbonatite, because it shows alignments of gangue minerals such as magnetite, apatite, or various silicates across the pipe. This is followed by the fracturing event of the Loic pipe in its center, which triggered the resurgence of the igneous activity and the emplacement of a second carbonatitic pulse along the fractures in the pipe, which forms what is called a transgressive carbonatite. And everything, all the different rock units in the Phalaborwa igneous complex are postdated by a series of dolerite dikes occurring in the northeast-southwest axis, and which have been estimated to be of Karoo age. A very important and interesting feature in the Loic pipe is that according to various geological studies, it has been proven that pyroxene-bearing pegmatoids, phosphorite, banded carbonatite, as well as transgressive carbonatite occurred almost, and placed almost synchronously. They have all been dated around 2060 million years old, and all the ages are within the error margin. Something I wanted to show you as well is the very cylindric geometry of the Loic pipe, as well as the alternation of the banded carbonatite and phosphorite layers, as you can see here, which is very important for the rest of this presentation. So about copper sulfides now. So copper sulfides in the Phalaborwa igneous complex are exclusively hosted by the Loic carbonatite and phosphorite intrusion, and are mainly composed of chalcopyrite, bornite, as well as valerite. Valerite is a very fine-grained brownish mineral composed of iron, copper, sulfur, magnesium, and aluminum. Two main points about the copper sulfides within the Loic intrusion make consensus. The first one is that the major part of the copper mineralization is hosted by small veinlet networks, which can be up to 10 meters wide within the transgressive carbonatite. And the second point is that the copper mineralization hosted by the banded carbonatite and the phosphorite only contributes to a very minor way to the total volume of the sulfides. The textures encountered in the banded carbonatite and phosphorite are sulfide patches and blebs, and these sulfides can also be observed aligned together with gangue minerals. Despite some point of consensus, let's say that more points are very, very controversial. And the first one is the following question: how many stages are there in the sulfide pyrogenesis within the Loic carbonatite phosphorite intrusion? A study by Johannes Giebel and co-workers in 2017 mentioned that sulfides crystallize in only one single stage, while Heinrich in 1970 rather suggests that that there is also a single stage, but that sulfides the difference in terms of texture related to a variation in temperature between the marginal zone and the core of the pipe. Other studies, such as a paper published by the Phalaborwa mining company staff in 1976, as well as other papers published in the 2000s, rather suggests two distinct stages, one magmatic, one hydrothermal. So as you can see, nobody really agrees on this specific point. Another controversial point is about valerite. Does it occur as coating? Is it an alteration mineral? What's the abundance of valerite within the pipe? Several studies revealed that valerite is present in very significant amount, while other ones just don't even mention it at all. So yeah, what's happening with this mineral? So the purpose of this project is first to identify the source or the sources of the base metals constituting the sulfides in the Loic intrusion. Then is to refresh the inventory and to constrain the relative timing of the different copper sulfide assemblages within the intrusion. Third is to identify and characterize the different ore-forming processes operating in the Loic carbonatite phosphorite intrusion. So to summarize, is to propose an updated model for the copper sulphides metallogenesis within this intrusion. To solve these problems, 5 different methods have been selected. The 3 first ones have been chosen for the ability to provide proper updated sulfide classification. And with these 3 methods, it has been expected to get, let's say, a very comprehensive data set to properly characterize the different sulfide textures. So it consists in first optical microscopy, mineral liberation analysis, as well as the 3D microfocus X-ray computed tomography, or microCT. It will be easier for the rest of the presentation. The 2 other methods are wall rock and in situ PGE analysis and stable isotope systematics, which have been proven to be very efficient to identify the different sources of the base metals, as well as to constrain the ore-forming processes for different ore deposits, in particular, and copper sulfide ore deposits. So let's move on to the sulfide texture characterization. So optical microscopy observation reveals the presence of 3 main texture categories. The first one is characterized by the disseminated grains of bornite within bonded carbonatite and phosphorite with chalcopyrite solutions as patches or exsolution lamellae. It has been observed that some chalcocite veinlets or exsolution may occur within these grains, and some covellite alteration along the boundaries of the grains can also be present. The second category is chalcopyrite veins, which can be pluricentimetric and are composed of chalcopyrite, of course, and show the presence of cubonite exsolution lath, which can be up to 100 micrometers wide. Some pyrite and pyrrhotite have also been observed in these veins, as well as you can see in this picture, fractures filled with magnetite and valerite. And the last category is composed of valerite occurring along fractures and cracks as well as along boundaries of the primary grains. As you can see here, typical bornite grains with chalcopyrite exsolutions, and variabilities here, really along the fractures. Yeah. So still about valerite, as you can see, mineral liberation analysis show exactly the same feature as microscopic observations, meaning valerites along fractures, but also along the boundaries of sulfides, and which looks like replacement features actually, and something else quite interesting is the presence of valerite along fractures within the gangue, so not directly associated with sulfides, primary sulfides, I mean. Another interesting feature for disseminated grains is, as shown by the block, the polishment on the left, is a preferential association of bornite grains with magnetite, with other gangue minerals as well, but with magnetite in particular, as you can see also with this on the block on the left, where you have these two disseminated grains associated with magnetite in gray-black, in apatite in purple. Something very interesting on the polishment on the right. Well, something maybe I need to clarify first. On this mount, there's a presence of a chalcopyrite vein here on the right. Unfortunately, due to the geometry of the drill core, it was not possible to include it in the mount. So what it's possible to observe here is the presence of kind of networks of chalcopyrite and bornite at the immediate proximity of the chalcopyrite vein, and something which looks like a dissolution process of gangue minerals, and a reprecipitation of sulfides filling the gaps, suggesting fluid circulation into cracks and small veinlets in the gangue, in the host rock. Very interesting feature with microCT. First of all, is that it doesn't show the same results than optical microscopy and mineral liberation analysis at all. And maybe the first thing is that microCT results show the domination of chalcopyrite over bornite in terms of primary sulfides, as you can see on this picture. And maybe it's more clear with these two heat maps, where there is chalcopyrite here, bornite there, so there's a clear domination of chalcopyrite over bornite. Maybe the second point is that instead of one texture, which is disseminated sulfides, microscopy showed the presence of three different ones. The first one is disseminated grains within the gangue, but the second and the third one haven't been observed with the microscope and mineral liberation analyzer. And these are elongated assemblages, as you can see here, and sulfide cumulates with 1 millimeter thick, approximately in this case. Something which hasn't been observed at all before. Another interesting point here is sphericity of the grains. As you can see here, grains can be considered as spheric, with a diameter below 700, 500 micrometers, while everything bigger than that has a kind of non-satisfactory sphericity. With this other banded carbonatite sample, you see exactly the same feature. This domination of chalcopyrite over bornite in terms of primary sulfides, as you can see here, these two heat maps. But the main difference actually is the fact is a concentration of valerite here, which is very important. And something also very interesting here is that valerite is exclusively present together with primary sulfides, such as chalcopyrite and bornite. And there is no presence of valerite veinlets as observed with the mineral liberation analysis. But otherwise, it's possible to see exactly the same texture. So sulfide cumulates disseminated grains, and sphericity pattern is exactly the same. Something interesting with a transgressive carbonatite sample, as you can see here, so it's on the right, there's a presence of a chalcopyrite vein. And something also interesting is the presence of disseminated sulfide alignments here, parallel to the vein. And it reminds me a little bit of the transgressive carbonatite block for mineral liberation analysis with mineral mapping. However, the main difference is that what we see here is that the sulfides at the proximity of the vein are classified as disseminated grains, which means that they don't have any, they have nothing to do, according to this classification, they have nothing to do with the vein itself. Otherwise, it would have been assimilated to the volume in red. So what's the mineralization, the mineral liberation analysis, showed is that there is a presence of very small fractures and veinlets, which allows the circulation of potential fluids, triggering the precipitation of the sulfides. So what it's possible to deduce from this map is that the fractures and the veinlets are smaller than the resolution of the microCT. So smaller than about 20 to 30 micrometers. Yeah, so again, the domination of chalcopyrite over bornite. Thanks to all this observation, it is possible to update the copper sulfide classification between three different main categories: magmatic sulfide layers, hydrothermal veins, and late-stage valerite. So maybe a small precision. All the drill cores which has been analyzed with a microCT has been drilled sub-horizontally into the Loic pipe. And I don't know if you noticed, but there was a presence of sub-perpendicular veins, mineral alignments. So sulfides are present as layers. So it's possible to deduce from these observations that we are in the presence of subvertical sulfide alignments. So yeah, so I think that these layers are actually parallel to the alternance of banded carbonatite and phosphorite. I showed you on the cut on the slide number 3. So the sulfide here are considered to be magmatic because they are trapped into the host rock. And they show the three textures I mentioned before. So the small side bornite and chalcopyrite grains with some grains, complex grains with both bornite and chalcopyrites, some flat elongated which grains, assemblages, it's more correct, which can reach a length of about 1 centimeter. And the last type is chalcopyrite and millimetric thick cumulates. The second main category consists in hydrothermal veins, which can be more than 1 centimeter wide, with adjacent sulfide networks within the surrounding gangue. And the last one is valerite, which can be considered at late stage, considering the different mineral association and its occurrence across cracks and veins and around the boundaries of the sulfide grains, but also within the gangue at the immediate proximity of the sulfides. Otherwise, as it has been possible to see with the microCT observation, there is no valerite veins alone in the gangue. So based exclusively on the textures, it's possible to come up with a provisional mineralization model, as I consider it. With first a magmatic stage, which is characterized by the successive intrusion of different melt pulses. And as you can see, with alternance of bonded carbonatite and phosphorite, as well as the fact that phosphorite preferentially in place along the boundaries with the host rock, that we have a progressively decrease in iron oxide, phosphate, and silicate contents from early stages to later ones. Another interesting point is that because we have in the different layers various variable chalcopyrite bornite proportions, it's possible to suggest that we're in the presence of several sulfide liquids involved, and each having its own chemical composition. Yes, and the different textures we see actually, and the difference between the sulfide layers observed with a microCT and the small grains disseminated within the gangue, as shown with mineral mapping with the MLA, is related to the variable magma flows during the emplacement of the phosphorite carbonatite intrusion. As a matter of fact, high magma flow rates prevent the coalescence of sulfide grains, which triggers a dissemination within phosphorite and bonded carbonatite, whilst low magma flow rates allows the binding of these different sulfide blebs in the magma and the formation of the different assemblages we've observed with a microCT analysis. The second stage is a hydrothermal one, which is characterized after the magmatic stage by fracturing of the pipe, mainly in its center, and circulation of high temperature hydrothermal fluids, which precipitated chalcopyrite with cubernitic solutions, which is followed by the third stage, last but not least, which is characterized by further fracturing of the pipe and fluid circulation. And all the sulfides, primary and hydrothermal sulfides in contact, have been altered and replaced by valerite. And actually, that's why we have a heterogeneous distribution of valerite within the pipe. That's why some studies noticed it and others didn't. Let's move on to the chemical part now. Some laser ablation work has been performed on sulfides and epoxy mounts. And two main features have been observed. The first one is the enrichment of palladium group PGEs over iridium group PGEs. And the second point is the low PGE concentration. So we can come with several points from these results. The first one, with this PPG enrichment of IPGE, is the presence of in the Loic carbonatite phosphorite intrusion of a monosulfide solid solution, intermediate solid solution system. So after the second point is that we're in the presence of a low degree partial melting. So after the melting of the source and the ascent of a sulfide liquid, this sulfide liquid separated into two different phases: monosulfide solid solution, iron-rich, and IPGE-rich, which remained at depth, and that's why we don't see any iron sulfides, or few, in the Loic intrusion, and a copper sulfide, copper-rich, and PPG-rich sulfide liquid, which further ascend and forms the sulfides we observed with microCT, MLA, and optical microscopy. So some wall rock PGE analysis has also been performed and show also a very, very low PGE content, which correlates with the observation made with sulfides. And it shows actually a very interesting feature. As you can see, there is a progressive depletion in PGEs from micaceous pyroxenite, which is the earliest rock to be in place, to transgressive carbonatite, which is the latest one. This suggests first that all these rocks have a common source, and secondly that we are in the presence of successive partial melting processes, which each of them extract PGEs and exhaust actually the source in terms of PGE concentration. That's why we almost have nothing anymore with the transgressive carbonatite. Let's move on to the isotope part. And let's start with a small method, with a couple of method slides. It has been decided to use both sulfide separates as well as in situ samples. So sulfide separates have been very easily obtained by crushing some piece of drill core, and intact sulfides have just been taken and processed. In situ samples, however, it has been a little bit more complicated. We tried we asked around for if it was possible to do some laser ablation work, and it was way too expensive. So we found out an alternative, which consists into simple drilling, micro drilling into epoxy mounts through a water droplet, of course, to avoid the contamination of the environment. And yeah, it's kind of cheap, it's quick, and also we can process the result by ion exchange chromatography to get rid of all the matrix, the trace elements, which might trigger some issues during the measurements. So there's a sample powder is then taken and put into a dissolution beaker. And from then, the procedure is the same for sulfide separates and drilled samples. It consists first into the dissolution with a mixture of HCl, HF, and HNO3. The samples are then dried and converted into chloride form, and afterwards the fractions of interest have been separated from the matrix by ion exchange chromatography. And we realized actually that 2 ion exchange chromatographies are necessary to obtain a satisfactory purity of the fractions. So the sample is put on the ion exchange resin, and the fractions of interest in the garbage have been eluted by adding several volumes of several type of acids at different concentrations. And then the fractions have been measured on multi-collector ICP-MS. Copper isotopes have been measured as a new plasma 2 multi-collector at UJ with the help of Henriette Öckermann. And the fractions have been diluted to 1 ppm and spiked with a nickel solution and measured with the standard sample bracketing method, which consists in the measurement, successive measurements of standard sample, etc., to correct the mass bias, which occurs during the measurement session. For ion isotopes, have been measured on the Thermo Fisher Neptune Plus multi-collector. It's exactly the same parameter at 1 ppm with nickel spike and standard sample bracketing, but in Lyon at the ENS CNRS in France. Concerning the results now of the isotope analysis. First of all, for copper, the first thing that we see here is that the variation range for in situ samples is much wider than for separates. Separates which range only from minus 0.64 to 0.39, while in situ samples range from minus 1.21 to 0.76, which is quite big. Moreover, as you can see, there is no correlation between sulfide types and the copper isotopic composition. Here, for instance, in situ samples with a simple bar like that, it's magmatic samples, stripes, hydrothermal ones, and cross alteration. So as you can see, there is absolutely no pattern. Several points can be made from these results. The first one is that when the presence of hypogean sulfides, considering the variation range of sulfide separates, so which is comprised between -1 and 1 per mil. Second point is that despite the fact that the variation range of separates is kind of small, there is still some variation, which suggests that the mental source is, in addition to be chemically heterogeneous, as we've seen with the variation in terms of chalcopyrite bore nitrations into the different sulfide layers, is obviously heterogeneous in terms of copper isotope composition. And the last point, when we observe the in situ samples, is that we are obviously in presence of small-scale isotope fractionation processes. Concerning ion isotopes now, so when I was taking the sulfide separates from the samples, there was some very nice rounded magnetite. It's just, yeah, so I just said, let's have fun, run one batch and measure them, and let's have a look and see how it looks like. And actually, it was, lucky for me, it was very, very important. First, we can see that there is a slight enrichment in heavy iron, so iron 56 over iron 54. And as we will see in the next slide, the ion isotope composition is very close to, it's the same actually, than with as a magmatic sulfides. That suggests, first of all, that this magnetite is of magmatic origin, as suggested by Lorenzo Milani in 2017. This hydral magnetite is actually crystallizing from the magma. Second point is that this magnetite precipitated in oxidized magma, which is actually quite logical, considering the fractional crystallization series, which after the crystallization of silicates leave slightly oxidized magma. And as you can see in the in situ samples, that we have this slight enrichment or near zero ion isotope composition for magmatic sulfides. And considering what we've seen with the mineral liberation analysis mineral maps, is that we have synchronous precipitation of magnetite in the magmatic sulfides. That's why they have the same signature and they are associated to each other. So the second interesting point here with iron composition in copper sulfides. First of all, let's start with wall rocks. There are two different groups. First one comprises banded carbonatite, phosphorite, micaceous pyroxenite, and is slightly enriched in iron 56. Second, exclusively composed of transgressive carbonatite, show an enrichment in iron 54, slight depletion in iron 56, depending on the point of view. Second point is that we have two clusters. So it suggests several things. The fact that we have similar values for banded carbonatite, phosphorite, and micaceous pyroxenite suggests that there's three rocks are of mantle origin, first of all, and then that they are coming from, as mentioned with the results for PGE analysis, of a low degree partial melting. Matter of fact, iron 56 is highly incompatible and preferentially fractionate into the magma. However, the slight the depletion in iron 56 of transgressive carbonatite may suggest another source for this rock, but that's purely speculation. A very interesting thing with in situ samples here is the depletion of hydrothermal sulfides, which might be linked actually to the transgressive carbonatite isotope composition. But in this case here, we suggest that hydrothermal sulfides result of the leaching at depth of magnetite and sulfides by high temperature hydrothermal fluids, which triggers a breakdown, the preferential removal of iron 54, and the subsequent precipitation of the remobilized material in chalcopyrite veins and other sulfides such as boronite and chalcopyrite into the small networks adjacent to the veins. So concerning the updated model now, so as mentioned, as suggested in the provisional model during the middle of this presentation, we have three stages. First of all, the magmatic one, which consists in the limited partial melting of isotopically and chemically as heterogeneous mantle source for the base metal budget, which is followed by the ascent of a sulfide liquid, which separate into a monosulfide solid solution, which remain at depth, and further ascent of a copper-rich sulfide liquid, which further differentiate into boronite and chalcopyrite during the ascent, and which forms a different texture, which are disseminated grains, elongated assemblages, and sulfide cumulates, depending on the magma flow. The second stage is a hydrothermal one, which consists, as I just mentioned, of the leaching of magnetite and magmatic sulfides, and the reprecipitation of the remobilized material as chalcopyrite veins and boronite and chalcopyrite in the small networks at the vicinity of these veins. And last but not least, third stage, alteration 1, which is characterized by the late stage fluid circulation and the desulfurization of magmatic and hydrothermal sulfides encounter in their transformation into phalaborite. And of course, this desulfurization is heterogeneously distributed within the pipe because of the heterogeneous fracturing, if I may say so. So considering the further work which has to be done, because actually I have the feelings that I have more questions now than answers compared to the beginning. The source of the hydrothermal material has to be further constrained. So despite the fact that I said that it's coming from the breakdown of magnetite and sulfide, so there is no petrographic evidence for that so far. So this point needs to be further investigated, so either by finding this petrographic evidence or propose an alternative. Second point is to investigate late-stage alteration processes as well as the sources of the late-stage fluids. That might be very complicated considering the complexity of phalaborite itself. And the last point is to make some further work on ion isotope composition of the different gangue minerals within the pipe to provide further information about the emplacement process or processes of the phosphorite, carbonatite intrusion. And what I've learned during this project, and maybe the most important point, is if we want to properly characterize copper sulfides with isotopes, it's necessary to use both iron and copper isotopes for copper sulfides, as well as both sulfide separates and in situ samples to constrain both isotopic fractionation processes at big and small scale. Moreover, this study revealed that sulfides are an excellent tracer for emplacement processes of phosphorite and carbonatite, which is actually very interesting for further work somewhere else. Thank you very much for your attention, and please feel free to ask any questions. Grant?
Loic, thank you so much. Please leave your slides shared, because I'm sure there'll be some questions on the slides.
Sure.
Just to remind everyone that if you do want to ask Loic a question, it's very simple. You can either type a question into Q&A window that you'll find on the bottom of your screen, or you can raise your hand, which you'll also find on the bottom of your screen, and then we'll unmute you and allow you to talk. While you think about questions, Lou Ashwell has already sent through a question. This is on WhatsApp. Thank you, Lou. And Lou asks Loic, do your results support a lithospheric or asthenospheric mantle source for your samples?
Very good question. I didn't consider this aspect, to be totally honest, but it's very likely that the source is lithospheric. However, this point has to be further investigated, in my opinion.
Okay, then we also have Robert, who is sitting in my office. Robert, do you have a question?
I've got a question to Loic. So, Loic, have you considered doing zinc isotopes on the same sulfide samples? And what if you were considering zinc isotopes, which I believe were planned to be set up in our lab, what do you think would zinc isotopes tell you in addition to the iron and copper isotopes?
Okay, so considering the sulfides we have, so copper and iron obviously more convenient since they are copper and iron sulfides. So for zinc isotopes so considering the trace element analysis which has been performed, and unfortunately I didn't have time to present the results, there is some zinc into the sulfides. So it's possible to use zinc isotopes. So the interesting thing with zinc isotopes is that they are not very sensible to redox processes, while it's absolutely not the case for iron and copper. So, for instance, in sulfide grains, I showed that in the grains themselves there might be some fractionation processes which might be related to the change in redox state. Zinc isotopes wouldn't show that. It means that we would have the original unaltered signature of the source. And that would be actually very interesting. So that would be the interest of zinc isotopes applied to Phalaborwa. But in a more general perspective, the main interest of zinc isotope is that they are not sensible to redox changes. Does it answer to your question, Robert?
Yeah. So you are basically saying that the zinc isotopes wouldn't really provide you with much more information than what you already have from the iron copper isotope. Is that right?
Yes, however, there is one point I would like to be sure, and it relates a little bit with Lou's question, is that I can be 100% sure with zinc isotopes what the source is, while with iron and copper, they evolve a little bit too much during the emplacement processes to constrain the source really properly. While I think that zinc isotopes can provide very good indication, clean indication at this point.
Thank you very much, Loic.
Great. Do we have any other questions for Loic? I don't see any hands up right now. George Henry, thanks you, Loic, for an excellent talk. Thank you for watching, George. Any other questions or comments for Loic? If you do, just raise your hand and we'll allow you to talk. Maybe what I can just add to both Robert and Lou's comment is that there have been some recent papers showing that zinc isotopes are a very good discriminator for lithospheric versus asthenospheric components in different kinds of magnets. So Loic, you got it spot on that zinc isotopes may be useful for that discrimination. Okay, I don't see any other questions at the moment. So Loic, thank you very much for that very, very detailed and very, very fascinating talk. Thank you for taking the time to make it. I'll also point out that amongst many other things that Loic is doing now in his postdoc, he's also setting up sulfide standards, or a whole range of standards for iron, copper, and maybe zinc isotopes as well. So to take this work on further and set up a whole set of standards that the international community can work on. And so, of course, if you have any interesting projects that may utilize iron, copper, or zinc isotopes, then Loic is your man, and we can do that work in the Wiggle. All right, so we're going to end off there. Of course, as usual, if anyone would like to stay on and ask Loic any questions, you're welcome to. You just need to raise your hand, and then we'll add you to the panelists. But before we let you go, I just want to inform you of the talk for next week, which I think will be interesting to a wide range of people. So you should be able to see my screen now. We have a talk by Alan MacDonald from the British Geological Survey, and he'll be talking about mapping groundwater recharge across Africa. And of course, you'll get the link for this talk in your inbox next Monday. Thank you, everyone. Thanks for joining, and thanks once again to CCIC for sponsoring these talks. And thank you, Loic, once again. We'll see you all next week. All the best.